once we put our Lewis structures together, the next thing we want to do is try to understand the shape of the molecule. The shape of the molecule is actually going to come into play as we start to understand how everything interacts more, okay? So we have this theory, VSEPR. It stands for valence shell electron pair repulsion. Because what happens is we have electrons, they're negative. They repel each other. So when molecules bond and they form their discrete molecules, they try to form shapes and arrange themselves in a manner that is going to minimize those repulsions. And so the electrons are going to push each other away as much as possible in order to minimize those repulsions. Okay, so we're going to look at 3 basic molecular shapes for this. We're going to look at linear, trigonal, and tetrahedral. Now, there's 2 more shapes that go beyond that, but those are beyond the scope of this level of a course, okay? If you tool around online, you might find things where you start to learn about violating the octet rule, expanding the octet, going beyond tetrahedral. Those exist, but they are not the scope of what we're doing right here. We are sticking to the octet rule, and we are only going up through tetrahedral geometry. All right, so to predict our shapes, we look at what is on that central atom, okay? We want to put them as far apart from each other as possible, and so we have this VSEPR theory, okay? When we look at VSEPR, we have to draw a full valid Lewis structure, but when we evaluate the geometry, we are only looking at the central atom. So only the bonds and lone pairs around the central atom matter for the geometry. Okay. Now, I've altered these slightly from the slides I put up online for you to download. I have moved over what was in the bottom right-hand corner to be over to the side so that my little head didn't cover everything up. All right, so what you'll see is in this left-hand corner, this is the orbital or electronic okay? So you'll see that in the corner of every slide. It's the orbital or the electronic geometry. This is governed by the total number of electron groups around the central atom, okay? You'll also see, this is in the right-hand corner for what is available for you to download. This is the molecular geometry, or the shape. Now, if everything is bonding, if there are no lone pairs on the central atom, the orbital and the molecular are exactly the same. But once we start putting lone pairs in, then things start to get a little bit crazy. All right, I also use this AXE notation. A is our central atom. X is a surrounding atom. And E is a lone pair, okay? All right, so 2 electron groups. We're gonna start with this AX2. So I have 1 central atom, 2 surrounding atoms. So I have a total of 2 electron groups around my central atom. Okay, so I have 2 X's plus 0 E's gives me 2, so 2 electron groups, okay? So what I have something that is considered linear, okay? So its orbital geometry is linear, and then its molecular geometry is also linear because everything's bonding, all right? So it looks like a straight line, all right? So this one that I built here has these little kind of bulbous things because I've had to put in some double bonds because an example of this one is carbon dioxide. Okay, so now here's my valid Lewis structure. All right, now I mentioned that when we evaluate the geometry, the only thing that matters is what's on the central atom. All right, now when we look at bonding groups, single bond is 1 group, double bond, 1 group, triple bond, 1 group. So I have a double bond here and a double bond here. So I have 2 groups. which is why it's actually easier to just count the number of surrounding atoms. So I've got carbon is my central atom. I have one oxygen. I have a second oxygen. So I have this AX2. So if you have a situation like this, no lone pairs, now we have linear orbital geometry and linear molecular geometry. Okay? Now, if I were to remove one of my bonding groups, and now I only have two things hooked together, like in the case of a carbon monoxide, I still just have a straight line. Two things, point A to point B, still just a straight line. All right, so we're done with that one. We can't do anything further with our 2 electron groups because we just get a straight line. So we'll move to 3 electron groups. Okay, so 3 electron groups. Now our orbital geometry is trigonal planar. When everything is bonding, our molecular geometry is still trigonal planar. All right, so trigonal for 3, planar for in the plane. Okay, we have a bond angle here between atoms of 120 degrees. Right, and so it looks like this. Okay, trigonal planar. I can squish it in the plane. Okay, so again, orbital geometry, trigonal planar, because I have 3 total electron groups. Okay, all right, so now here's an example of this one. Okay, so I have that central atom, and I have 1, 2, 3 atoms. It's bonded around. So there is my trigonal planar. No lone pairs. Okay. Now I can take off one and still be left with at least 3 things hooked together. All right. So now we still have 3 electron groups. All right. But now I have 2 bonding groups and 1 lone pair. So 2 plus 1, so 2 X's and 1 E, gives me a total of 3 electron groups. So again, the orbital or electronic geometry is governed by the total number of electron groups. So our orbital geometry here is still trigonal planar. But now that I have removed something that's bonding and added a lone pair, the shape of my molecule is considered bent. Okay? If you look this up online, sometimes you'll see bent, V-shaped, angular. Bent is the most common. So it'll look like this. Okay, so I've got these 3 things hooked together and it's bent. This little paddle on top represents the lone pair. All right, so it looks like this. Now our bond angle here is less than 120 degrees because what happens is this lone pair, again, it is going to try to minimize repulsion. So it's going to spread itself out as much as possible to minimize repulsions. So as that spreads out, what that does is it squishes the bond angle down, so it's less than 120 degrees. How much less than varies from molecule to molecule. So you just need to know that it's less than. So an example here is ozone. I'm only going to draw one of the 2 resonance structures because each resonance structure has identical geometry. So again, when we evaluate the geometry, we only care about what's around the central atom. So my central atom here, I have my central atom. I have 1, 2 oxygens, so there's my 2 bonding groups, and 1 lone pair. So that's where I get this. So my orbital geometry is going to be trigonal planar. My shape or my molecular geometry is bent. Okay, if I remove something else from it, once again, now I just have 2 things hooked together, so we're done with this one. So that moves us into our last consideration, 4 electron groups. So when we have 4 electron groups, our orbital geometry is going to be tetrahedral, okay? Because it looks like a tetrahedron. So here's an example of what it looks like. So this one is not flat anymore. So as you can see, I can't squish it between my hands. It's not flat anymore, all right? Okay. All right, so our tetrahedral, 4 total electron groups. So an example of this one is methane, CH4. So I've got my carbon in the center and I have 1, 2, 3, 4 things that are bonded around it. So I have 4 electron groups. They're all bonding. So my shape is also tetrahedral. Remember, when everything's bonding, the orbital and molecular geometries are exactly the same. Okay? All right. Our bond angle here is 109.5. So this would be 109.5 degrees for the bond angle. All right, if I pull off an atom, replace it with a lone pair, I still have at least 3 things hooked together. So now we can move on to having a lone pair there. All right. So now we still have tetrahedral orbital geometry because I still have 4 electron groups. 3 bonding plus 1 lone pair still gives me 4 electron groups. Okay, so now same sort of thing. When I add in a lone pair, what happens is it takes up space and it squishes the bond angle down. So our bond angle now is less than 109.5. Okay. So our orbital geometry is still tetrahedral, but now our molecular geometry, or our shape, is considered trigonal pyramidal because it looks like a little squat 3-pronged pyramid with a lone pair sticking up. All right. An example of this one is ammonia. So I have my nitrogen, hydrogens, and my lone pair there. So I have 1, 2, 3 bonding groups and 1 lone pair. We can still remove an atom and replace it with a lone pair and keep with 4 electron groups. So again, 4 groups because I have 2 bonding plus 2 lone pairs gives me a total of 4. Okay, so 4 electron groups. So my orbital geometry is still tetrahedral. Okay, but now the shape of my molecule is considered bent. So it looks like this. All right, so here's my 3 things bonded together. Again, bond angle is less than 109.5 because it squishes that bond angle together. Okay, an example of this one is water. All right, so we get oxygen. This is also why I draw my water like this, because I know that water is bent. So I have 1, 2 groups that are bonded to the oxygen and 1, 2 lone pairs. Okay, and so there is a summary of all of those. So now let's see if we can apply some geometry to some of these structures. Okay. So here we'll do the Lewis structure. We'll do the orbital and molecular. All right, so this one looked like this. Okay, so I have 4 bonding groups and no non-bonding groups around my central atom. So I have that AX4 situation. So my orbital geometry is tetrahedral. And my molecular geometry, it's all bonding, so it's also tetrahedral. Okay. All right, so there's that one. Okay. So central atom, 3 things bonded around it. This is our trigonal planar. Everything's bonding, so it's also trigonal planar for molecular. Okay. All right. Here we'll do this one. All right, now we've got some lone pairs. All right, so I have 2 bonding, 2 non-bonding. So how many total electron groups is that? Well, 2 plus 2 is 4, so it's 4 total electron groups, which is tetrahedral for our orbital geometry. Which means that our molecular geometry, though, this time is different because I have lone pairs. So when I have 2 bonding and 2 non-bonding, now I have bent for my molecular geometry. Okay? All right, so here's a few more. do the Lewis structure, the orbital, the molecular. Okay, so I want you to try these before I give you the answers. All right, let's see how you did. So this is tetrahedral because it's 4 electron groups. And this is the trigonal pyramidal. Okay. This one we only have 2 things hooked together. The only thing it can be is linear. And then carbon dioxide. I have 2 bonding groups around my central atom, no lone pairs, so it's linear and linear. Okay, so that is how we determine shape.